Let us begin slowly, and let us remember where we are in the landscape of abstract algebra. A group is a set of objects together with a way of combining them. The combination must behave in a stable and predictable way. There must be an identity element, every element must have an inverse, and the order in which we place parentheses must not matter. These simple rules create a surprisingly rich world. They allow us to speak about symmetry, motion, rearrangement, arithmetic, geometry, and structure, all using one common language. In the beginning, group theory often feels like a study of examples. We meet the integers under addition. We meet rotations of a polygon. We meet permutations of a finite set. We meet matrices that can be multiplied and inverted. But as we go deeper, group theory becomes less about isolated examples and more about how groups relate to one another. We ask how one group can contain another. We ask how one group can be mapped into another. We ask how a group can act on a set. We ask how a large group can be built from smaller pieces. And we ask how a group can be simplified without losing its essential information. This lecture is about those deeper organizing ideas. We will move gently through quotient groups, isomorphism theorems, products, group actions, orbits, stabilizers, permutation groups, Cayley's theorem, and finally Sylow theory. These are among the central tools of a first serious course in group theory. They are not just individual topics. They form a connected story. The story is this: groups can be understood by how they collapse, how they act, how they decompose, and how their finite structure is controlled by prime numbers. Let us pause and reflect on that sentence. A group can collapse through a quotient. A group can act by a moving object. A group can decompose into independent parts. And a finite group can often be studied through the prime power pieces hidden inside it. We begin with quotient groups. Normal subgroups and quotient groups suppose we have a group, and inside it we have a subgroup. A subgroup is a smaller group sitting inside the larger group. It contains the identity element, it is closed under the group operation, and it contains inverses of its own element. At first, it is tempting to believe that every subgroup should allow us to divide the larger group by that subgroup. After all, in arithmetic, we often quotient by some relation and obtain a cleaner object. We identify things that differ by a multiple of some number. We collapse certain differences and keep only the remaining pattern. But in groups, not every subgroup behaves well enough to support this kind of division. The issue is that groups may be non-commutative. That means the order of multiplication can matter. Multiplying by something on the left can produce a different result from multiplying by the same thing on the right. Because of this, a subgroup may sit inside the larger group in an asymmetric way. When we form cosets of a subgroup, we are trying to group the elements of the large group into blocks. Each block is obtained by multiplying the subgroup by some element of the large group. But there are two natural ways to do this. We can multiply on the left or on the right. In a commutative group, these two ways always agree. In a non-commutative group, they may not. This is the first warning sign. If left cosets and right cosets do not align properly, then the set of cosets may not inherit a well-defined group operation. We might try to multiply one coset by another, but the answer may depend on which representative elements we choose. That is not acceptable. A quotient group must be a group, and a group operation must be unambiguous. So we need a special kind of subgroup. We need a subgroup that is compatible with multiplication in the surrounding group. Such a subgroup is called normal. A normal subgroup is not merely a subgroup. It is a subgroup that sits evenly inside the group. It is stable under the internal symmetries of the group. If we move the subgroup around by conjugation, it returns to itself. In more informal language, the subgroup looks the same from every position inside the group. It is worth repeating this idea in several ways. A normal subgroup is a subgroup that allows left and right cosets to match. A normal subgroup is a subgroup that can be collapsed without ambiguity. A normal subgroup is a subgroup that is compatible with the multiplication of the larger group. A normal subgroup is precisely the kind of subgroup needed to build a quotient group. Now let us think about quotient groups themselves. A quotient group is formed by taking a group and collapsing a normal subgroup to the identity. More generally, we treat two elements of the original group as equivalent if they differ by an element of the normal subgroup. The elements of the quotient group are not individual elements of the original group. They are cosets. They are blocks of elements. Each coset represents a whole collection of original group elements. In the quotient, we no longer distinguish among elements that lie in the same coset. We remember only the broader position of the coset. This is why quotienting is often described as collapsing structure. But it is not chaotic collapsing. It is controlled collapsing. We collapse exactly the part of the group described by the normal subgroup, and we preserve a meaningful group structure on the remaining collection of cosets. Think of a quotient group as a blurred version of the original group. Certain fine details disappear. The normal subgroup becomes invisible, but the remaining pattern still has a group operation. The quotient remembers how the larger blocks interact. Let us pause and reflect. Normal subgroups answer the question, what can we safely ignore? Quotient groups answer the question, what remains after we ignore it? This is one of the deepest ideas in algebra. We learn a structure not only by studying what it contains, but also by studying what happens when some part of it is deliberately collapsed. The first isomorphism theorem. Now we turn to one of the most important results in group theory, the first isomorphism theorem. To understand this theorem calmly, let us begin with homomorphisms. A group homomorphism is a structure-preserving map from one group to another. It sends products to products. It respects the group operation. It may lose information, but it loses information in an organized way. Whenever we have a homomorphism, we can ask two natural questions. First, what does the map send to the identity element of the target group? The answer is called the kernel. Second, what elements of the target group are actually reached by the map? The answer is called the image. The kernel measures collapse. The image measures what remains visible. This is a very important sentence, so let us say it again in a slightly different way. The kernel is a part of the original group that the homomorphism cannot distinguish from doing nothing. The image is a part of the target group that the homomorphism actually produces. The kernel tells us what information is lost. The image tells us what information survives. The first isomorphism theorem says that these two ideas are perfectly connected. If we take the original group and quotient out by the kernel of a homomorphism, the resulting quotient group is essentially the same as the image of the homomorphism. In words, the theorem says, once we collapse exactly what the homomorphism collapses, the remaining structure is precisely the structure that appears in the image. This is an extraordinarily natural idea. Imagine a homomorphism as a machine that takes elements from one group and sends them into another group. Some elements become indistinguishable because their difference lies in the kernel. The kernel is exactly the set of elements that vanish under the map. If we decide in advance to identify all elements that the homomorphism cannot distinguish, then the map becomes faithful in the quotient. Nothing further is lost. This is what we mean by factoring through a quotient. The original homomorphism can be understood as a two-step process. First, collapse the original group by the kernel. Second, identify the resulting quotient with the image inside the target group. Let us repeat this carefully. A homomorphism from a group to another group may fail to be one-to-one. The reason it fails to be one-to-one is measured by its kernel. If we quotient the domain by that kernel, then the failure disappears. The quotient group then matches the image. This matching is not accidental. It is canonical and structural. The first isomorphism theorem is therefore a bridge. On one side, we have maps between groups. On the other side, we have quotient groups. The theorem tells us that every homomorphism secretly contains a quotient construction. This is why kernels are always normal subgroups. They must be normal because they are exactly the subgroups through which quotienting is possible. The kernel of a homomorphism is not just any subgroup, it is a subgroup that can be collapsed while preserving group structure. Let us pause and reflect. Quotient groups arise when we choose a normal subgroup to collapse. Homomorphisms naturally collapse their kernels. The first isomorphism theorem says these are the same phenomenon seen from two different directions. From the quotient point of view, we choose what to collapse. From the homomorphism point of view, the map tells us what it collapses. The theorem says that after this collapse, what remains is the image. This idea appears again and again throughout algebra. It appears in rings, modules, vector spaces, topology, category theory, and many other places. Whenever we have a structure-preserving map, we ask what it kills, what it preserves, and how the quotient by what it kills relates to what it preserves. For groups, the first isomorphism theorem is the cleanest expression of this principle. The second and third isomorphism theorems are often introduced as technical results. They involve subgroups, normal subgroups, products of subgroups, intersections, and quotients. But at their heart, they are organizational tools. They help us compare different ways of collapsing structure. Let us approach them gently. Suppose we have a group, and inside it we have several subgroups. Some of these subgroups may be normal. Some may not. We may want to combine subgroups. We may want to compare a subgroup with a quotient. We may want to understand what happens if we collapse one subgroup first and then look at another. The second isomorphism theorem is about how a subgroup interacts with a normal subgroup of a larger group. It tells us that if we combine a subgroup with a normal subgroup and then quotient by the normal subgroup, the result can be understood entirely inside the original subgroup, after collapsing the part of the normal subgroup that already lies inside it. This sounds technical, so let us translate the intuition. Imagine one subgroup as the region we care about, and imagine a normal subgroup as the region we plan to collapse. When we look at their combined effect in the larger group, we do not need to understand everything globally. We can instead look inside the subgroup we care about and collapse only the overlap with the normal subgroup. The theorem says that these two perspectives give the same structure. So the second isomorphism theorem is a comparison principle. It compares collapsing after combining with combining after restricting attention. It tells us that the quotient structure obtained in the larger group can be understood through a smaller, more local quotient. Let us say this again more softly. If a normal subgroup represents information to be ignored, and another subgroup represents information we want to study, then the second isomorphism theorem tells us how these two tasks interact. It tells us that ignoring information globally corresponds to ignoring the overlapping information locally. Now let us turn to the third isomorphism theorem. The third isomorphism theorem is about collapsing in stages. Suppose we have a normal subgroup inside another normal subgroup, both sitting inside a group. We might first collapse the smaller subgroup, producing a quotient group. Inside that quotient, the larger subgroup becomes a normal subgroup as well. Then we can collapse again. The third isomorphism theorem says that collapsing in two stages gives the same result as collapsing directly by the larger subgroup. This is a deeply intuitive principle. If you erase fine details first, and then erase broader details, the final picture is the same as if you had erased the broader details from the start. The theorem makes this precise for groups. It is worth repeating. The third isomorphism theorem says that quotienting can be done step by step, provided the normality conditions are correct. If one normal subgroup lies inside another, then first quotienting by the smaller one and then quotienting by what remains of the larger one is equivalent to quotienting by the larger one immediately. This theorem helps us organize chains of normal subgroups. It is especially important in the study of composition series, solvable groups, and finite group structure. But even before those topics, it teaches a simple lesson: quotienting behaves coherently. Let us pause and reflect on all three isomorphism theorems. The first theorem connects homomorphisms with quotient groups. The second theorem compares a subgroup with the quotient of a larger group. The third theorem explains quotienting in stages. All three theorems are about controlled collapse. All three explain how structure survives when part of a group is identified with their identity. All three help us avoid manipulating elements blindly. They allow us to see the architecture of the group. Direct products and direct sums of groups, we now shift from collapsing groups to building groups. A quotient group is made by taking a group and simplifying it. A direct product is made by taking smaller groups and assembling them into a larger one. The basic idea is very simple. Suppose we have two groups. We can form a new group whose elements are ordered pairs, where the first coordinate comes from the first group and the second coordinate comes from the second group. To combine two such pairs, we combine their first coordinates using the operation of the first group, and we combine their second coordinates using the operation of the second group. This is called component-wise operation. Component-wise operation means that each part behaves independently. The first component does not interfere with the second. The second component does not interfere with the first. Each coordinate follows its own group law. This construction gives a direct product. The direct product is a way of building a larger group from smaller groups that act side by side. It is like putting two independent machines together. Each machine continues to operate as before, but now we view them as one combined system. Let us repeat the idea. In a direct product, an element has multiple components. Multiplication happens separately in each component. The identity element is formed from the identity elements of the component groups. Inverses are found component by component. The whole structure is a group because each part is a group. This construction extends beyond two groups. We can take products of many groups, even infinitely many. When the family is finite, direct products and direct sums often look the same for many familiar group theoretic purposes. But for infinite families, there is an important distinction. A direct product allows arbitrary choices in all components. A direct sum, in the usual algebraic sense, restricts attention to elements that are non-trivial in only finitely many components. In other words, most components must be identity elements. The direct product is larger. The direct sum is more controlled. The direct sum is often the right construction when we want finite support, meaning that each element carries only finitely much active information. Let us now think about decomposition. Sometimes a group is not merely constructed as a direct product. Sometimes a group that is already given to us can be recognized as a direct product internally. This means the group contains subgroups that behave like independent parts. Their elements commute with elements from the other parts in the appropriate way, their overlap is minimal, and together they generate the whole group. When this happens, we say the group decomposes into independent components. This is an important structural insight. Instead of studying one complicated group all at once, we may study its factors separately. If the factors are simpler, the group becomes more understandable. Direct products therefore serve two roles. They are constructions, because they build large groups from small groups. They are also decompositions, because they help us recognize when a large group is made of independent smaller pieces. Let us pause and reflect. Quotients simplify by collapsing. Products build by combining. Isomorphism theorems tell us when two constructions give the same structure. Together, these ideas begin to reveal group theory as an architecture of structure. Collapse here, build there, compare carefully, and understand what remains unchanged. Group actions and orbits. We now arrive at one of the most powerful ideas in all of group theory, group actions. A group action is a way for a group to move objects. The objects do not have to be elements of the group itself. They may be points in space, vertices of a polygon, colors of a cube, roots of a polynomial, subgroups of another group, or even functions. The group provides symmetries or transformations, and the set provides the things being transformed. To say that a group acts on a set means that each group element determines a transformation of the set, and these transformations are compatible with the group operation. Doing one group element and then another should correspond to doing their product. The identity element should do nothing. That is the entire idea in words. A group action turns abstract group elements into motion. This is one reason group actions are so important. Groups can feel abstract when we study them only through multiplication tables or axioms. But when a group acts, we see what its elements do. We see movement. We see symmetry. We see rearrangement. Let us consider a familiar example. The rotations of a square act on the four corners of the square. Each rotation moves each corner to another corner. Some rotations move every corner. The identity rotation moves none. The group operation corresponds to performing rotations one after another. This is a group action. Another example comes from permutations. A permutation group acts on the set it permutes. Each permutation simply sends each object to its new position. This is perhaps the most direct example of a group action. Group actions also occur in geometry. Symmetry groups act on geometric figures. They may rotate, reflect, translate, or otherwise transform objects while preserving some structure. They occur in combinatorics. A group may act on colorings, arrangements, necklaces, graphs, or configurations. By studying the action, we can count objects up to symmetry. They occur inside group theory itself. A group acts on itself by left multiplication. It may act on itself by conjugation. It may act on its subgroups by conjugation. These internal actions reveal deep information about the group. Now let us define two central concepts attached to a group action: orbits and stabilizers. The orbit of an object is the collection of all positions that object can reach under the action of the group. If we start with one object and apply every possible group element, the set of all results is the orbit of that object. The orbit is the world accessible from that object under the group action. Let us repeat this. An orbit is a movement class. It tells us which objects are connected by the action. Two objects lie in the same orbit if some group element can move one to the other. Orbits partition the set into regions of mutual reachability. This is a calm but important idea. A group action may not mix the whole set together. It may split the set into several orbits. Inside one orbit, all objects are related by the group. Between different orbits, the group cannot move objects. Now the stabilizer. The stabilizer of an object is the collection of group elements that leave that object fixed. These group elements may move other objects, but they do not move the chosen one. If the orbit measures movement, the stabilizer measures stillness. This contrast is beautiful. The orbit says, where can the object go? The stabilizer says, which symmetries keep it where it is. In the square example, consider one corner. The rotations of the square move that corner around the four corners. Only the identity rotation leaves that specific corner fixed if we consider rotations only. But if we include reflections, then there may be additional symmetries that keep a chosen vertex fixed while moving other parts of the square. The stabilizer depends on both the group and the object. Let us pause and reflect. A group action gives motion. An orbit records possible destinations. A stabilizer records symmetries that fix a point. Together, orbit and stabilizer express a balance between movement and internal symmetry. This balance becomes precise in the orbit stabilizer theorem. Orbit stabilizer theorem. The orbit stabilizer theorem is one of the most useful counting principles in group theory. It says that, for a finite group acting on a set, the size of the group is the product of the size of the orbit of an object and the size of the stabilizer of that object. Let us say this without symbols slowly. If we fix one object, then every group element does one of two things from our point of view. It moves the object to some position in its orbit, and it may also contain some extra symmetry that leaves the final position unchanged. The total number of group elements can be counted by first counting where the object can go, and then counting how many group elements produce each such destination. The stabilizer tells us how many group elements produce the same movement of the chosen object. This is the key intuition. If the stabilizer is large, then many group elements leave the object unchanged, and therefore the orbit is smaller. If the stabilizer is small, then fewer group elements are wasted on fixing the object, and the orbit is larger. Movement and fixed symmetry balance each other. Let us repeat the principle in several ways. A large stabilizer means little movement. A small stabilizer means more movement. The orbit measures how far the object can travel. The stabilizer measures how much of the group remains invisible at that object. Their sizes together account for the whole group. This theorem is not merely a formula. It is a way of thinking. Consider again rotations of a square acting on its corners. If we focus on one corner, the orbit consists of all four corners. Under rotations alone, only the identity fixes that corner. So the group is completely accounted for by the four possible destinations of that corner. Now consider rotations of a square acting on the center of the square. The center does not move at all. Its orbit has only one object. The stabilizer is the entire rotation group. This also fits the principle, no movement means all symmetry remains as stabilizer. Consider permutations of a set acting on the elements of the set. If the full permutation group acts, any chosen element can be sent to any other element. Its orbit is the whole set. The stabilizer consists of all permutations that keep that chosen element fixed while rearranging the remaining element. Again, the group size divides naturally into the number of possible destinations and the number of ways to act after fixing the destination. The orbit stabilizer theorem is often the first moment when students feel that group actions are not just decorative. They are computational and conceptual tools. They allow us to count symmetries. They allow us to classify positions. They allow us to reduce group questions to questions about orbits and stabilizers. Let us pause and reflect again. Group actions translate abstract algebra into motion. Orbits describe movement. Stabilizers describe fixed symmetry. The orbit stabilizer theorem says that, in finite settings, movement and fixed symmetry exactly account for the size of the acting group. Permutation groups. In Cayley's theorem we now move toward permutation groups. A permutation is a rearrangement of a set. A permutation group is a group whose elements are permutations, and whose operation is composition of permutation. Permutation groups are central in group theory for a simple reason: they are concrete. A permutation does something visible. It sends each element of a set to another element. It rearranges labels, positions, or objects. In the early study of groups, permutations were not just examples. They were one of the original motivations for the entire subject. The study of solutions of polynomial equations led mathematicians to study how roots could be permuted while preserving algebraic relations. From that study, group theory emerged. Even now, permutation groups remain fundamental. They provide a bridge between abstract algebra and combinatorics, geometry, and computation. Any time a group acts on a set, it gives rise to a permutation representation. Each group element acts as a permutation of the set. The action may not distinguish all group elements, but it still turns group elements into rearrangement. This brings us to Cayley's theorem. Cayley's theorem says that every group can be represented as a group of permutations. In plain language, every abstract group can be realized concretely as a group of rearrangements of some set. The set can be the group itself. The group acts on itself by left multiplication. Each group element defines a permutation of the underlying set of group elements, because multiplying by a fixed group element rearranges the group without losing or duplicating anything. This action is faithful, meaning that different group elements give different permutations. Therefore, the original group can be identified with a subgroup of a permutation group. This is a profound result. It says that permutation groups are universal. They are not merely examples among groups. They are broad enough to contain copies of all groups. Let us repeat this slowly. Every group, no matter how abstract it first appears, can be viewed as a group of permutations. Every group can act on itself in a way that reveals its multiplication through rearrangement. Abstract structure can be represented concretely. This does not mean that every group is best studied as a permutation group. Sometimes other representations are more efficient. Matrix groups, quotient groups, presentations, or actions on geometric objects may be more natural. But Cayley's theorem shows us that permutation representation is always possible. It gives psychological comfort as well as mathematical power. If a group feels too abstract, remember, it can be made into a group of permutations. Its elements can be interpreted as rearrangements. Its operation can be interpreted as composition of rearrangements. Its abstract law has a concrete model. Let us pause and reflect. Group actions lead naturally to permutation groups. Cayley's theorem tells us that every group acts faithfully on itself by permutations. So the abstract and the concrete are not separate worlds. They are connected by action. Sylow theorems and finite group structure. We now arrive at Sylow theory, one of the great organizing tools for finite groups. Finite groups can be mysterious. A group may have many elements and a complicated multiplication law. But the number of elements in a finite group is not just a size. It carries arithmetic information. In particular, its prime factorization strongly influences the structure of the group. Sylow theory studies finite groups through prime power subgroups. Let us begin gently. Suppose a prime number divides the size of a finite group. Then one may ask whether the group contains elements or subgroups reflecting that prime. Cauchy's theorem gives an early answer. If a prime divides the size of a finite group, then the group has an element whose order is that prime. Sylow theory goes further. Instead of looking only for individual elements of prime order, it looks for large subgroups whose sizes are powers of a prime. These are called Sylow subgroups. More precisely, for a chosen prime, a Sylow subgroup is a subgroup whose size is the largest power of that prime dividing the size of the whole group. It is the biggest possible prime power subgroup associated with that prime. This description is entirely about finite group structure. It says, choose a prime dividing the group size and look for the largest subgroup whose size is controlled only by that prime. The Sylow theorems then tell us three fundamental things. The first Sylow theorem is an existence theorem. It says that these largest prime power subgroups actually exist. If a prime power divides the size of the group in the relevant maximal way, then the group contains a subgroup of that size. This is already remarkable. The arithmetic of the group order forces the existence of internal subgroup structure. Let us repeat. The first Sylow theorem says that prime powers appearing in the size of a finite group are not merely numerical accidents. They are reflected inside the group as actual subgroups. The second Sylow theorem is a conjugacy theorem. It says that all Sylow subgroups associated with the same prime are conjugate to one another. In more intuitive terms, any two such subgroups are the same kind of object, viewed from different positions inside the group. Conjugacy is the group theoretic way of saying that two subgroups are internally symmetric versions of one another. If one subgroup can be moved to another by conjugation, then the larger group sees them as structurally equivalent. So the second Sylow theorem tells us that Sylow subgroups for a fixed prime are not scattered randomly. They form one conjugacy family. The third Sylow theorem is a counting theorem. It gives restrictions on the number of Sylow subgroups associated with a given prime. This number must divide a certain part of the group order, and it must leave remainder 1 when divided by that prime. The exact technical statement is usually written symbolically, but the intuition is this: the number of Sylow subgroups is heavily constrained. It cannot be arbitrary. It must satisfy both divisibility and congruence conditions. These constraints are extremely powerful. In many finite group problems, we begin with the order of the group. We factor it into primes. Then we apply Sylow theory to determine how many Sylow subgroups of each type could exist. Often, the numerical restrictions force one of these numbers to be 1. When there is exactly one Sylow subgroup for a given prime, that subgroup is normal. This is one of the most useful consequences of Sylow theory. A unique Sylow subgroup is normal because conjugation sends Sylow subgroups to Sylow subgroups, and if there is only one, it must be sent to itself. So uniqueness implies normality. And normality, as we have already seen, opens the door to quotient groups. Let us pause and notice the connection. We began with normal subgroups and quotients. We learned that normal subgroups are the pieces that can be collapsed. Now Sylow theory often helps us prove that certain subgroups are normal. Once a Sylow subgroup is known to be normal, quotient methods become available. The story is connected. Sylow theory is not an isolated final chapter. It returns us to normal subgroups, quotient groups, homomorphisms, and structure. Let us consider the broad use of Sylow theory in classification. Suppose we want to understand all groups of a certain finite order. Sylow theory helps by limiting the possible subgroup arrangements. It may show that a group must have a normal subgroup of a certain size. Then the group can be studied through that subgroup and its quotient. Sometimes this reduces the classification to smaller groups. Sometimes it shows that the group is a direct product or semi-direct product. Sometimes it proves that no complicated structure is possible. In this way, Sylow theory turns arithmetic into algebra. Prime factorization of the group order becomes a map of possible subgroup structure. Let us repeat the 3 Sylow principles in common language. First, Sylow subgroups exist. Second, Sylow subgroups for the same prime are all conjugate. Third, the number of Sylow subgroups is restricted by arithmetic conditions: existence, conjugacy, and counting. These 3 words are a good way to remember the Sylow theorems. Existence tells us that the relevant subgroups are there. Conjugacy tells us that they are all related. Counting tells us how many there can be. Together, they provide one of the strongest tools for analyzing finite groups. A slow unifying summary, let us now bring everything together. We began with the idea of quotient groups. A quotient group is formed by collapsing a normal subgroup. The normal subgroup is a part of the group that can be safely identified with the identity without destroying the group structure. Not every subgroup can be used in this way. Normality is precisely the compatibility condition needed for quotienting. A quotient group is a group of cosets. Its elements are not single original elements, but blocks of original elements. In quotienting, we deliberately forget certain distinctions. We collapse structure in a controlled way. Then we move to the first isomorphism theorem. A homomorphism is a structure-preserving map between groups. Its kernel records what gets collapsed. Its image records what survives. The first isomorphism theorem says that if we quotient the domain by the kernel, the result is essentially the image. This is the principle of factoring through a quotient. It is worth repeating: kernels measure collapse, images measure surviving structure, and the first isomorphism theorem says these 2 are joined by a quotient. Then we considered the second and third isomorphism theorems. These are organizational tools. The second theorem explains how subgroups interact with quotient. The third theorem explains how quotients behave when taken in stages. Both theorems tell us that collapse is not arbitrary. It has internal order. After that, we changed direction and studied direct products and direct sums. Instead of collapsing groups, we built larger groups from smaller ones. In a direct product, elements have components, and the operation is performed component by component. Such groups represent independent algebraic systems placed side by side. Direct sums are similar, but in infinite settings they impose a finite support condition. Direct products help us construct groups. They also help us recognize decomposition. If a group is made from independent parts, we can study those parts separately. Then came group actions. A group action is a way for a group to move objects. It turns abstract group elements into transformations. This idea connects group theory to geometry, combinatorics, symmetry, and internal group structure. From actions we obtained orbits and stabilizers. The orbit of an object is the collection of places it can be moved. The stabilizer is the collection of group elements that leave it fixed. The orbit measures movement. The stabilizer measures stillness. The orbit stabilizer theorem then gave us a counting principle. For a finite group action, the size of the group is accounted for by the size of the orbit and the size of the stabilizer. Large stabilizers correspond to small orbits. Small stabilizers correspond to large orbits. Movement and fixed symmetry balance each other. Then we considered permutation groups. A permutation group is a group of rearrangements. These groups are concrete and central. Whenever a group acts on a set, it gives permutations of that set. Cayley's theorem tells us that every group can be represented as a group of permutations, because every group acts on itself by left multiplication. This theorem reassures us that abstract groups can always be made concrete. Every group can be seen as a group of rearrangement. Finally, we arrived at Sylow theory. Sylow theory studies finite groups through the prime powers dividing their orders. It tells us that maximal prime power subgroups exist, that they are conjugate for a fixed prime, and that their number is arithmetically restricted. These theorems are essential for understanding finite group structure. Sylow theory often reveals normal subgroups. Normal subgroups lead to quotient groups. Quotient groups connect to homomorphisms through isomorphism theorems. Group actions explain conjugacy and counting. Permutation representations show that every abstract group can act concretely. So the ideas are not separate. They form one woven fabric. Normal subgroups teach us what can be collapsed. Quotient groups teach us what remains after collapse. Homomorphisms teach us how groups communicate. Isomorphism theorems teach us that different descriptions may carry the same structure. Products teach us how groups can be assembled. Actions teach us how groups move things. Orbits and stabilizers teach us how movement and fixed symmetry balance. Permutation groups teach us how abstract structure becomes rearrangement. Sylow theorems teach us how prime numbers govern finite groups. Let us pause one final time. The deeper lesson of group theory is that structure can be studied from many angles. We may look inside a group at its subgroups. We may look outside through its homomorphisms. We may simplify it through quotients. We may build it through products. We may watch it move a set through an action. We may represent it as permutations. We may analyze its finite size through primes. Each viewpoint reveals something different, but they all speak about the same underlying object. A group is not just a set with an operation. It is a world of symmetries, collapses, movements, and decompositions. And as we move through group theory, we learn to ask gentle but powerful questions. What part of this group can be ignored without losing structure? What map reveals its essential image? What normal subgroup lies hidden inside it? What objects does it act on? What remains fixed? What can move? Can the group be decomposed into independent parts? Can it be represented concretely? What do the primes dividing its size force it to contain? These questions guide the subject. They also calm the subject. Instead of seeing group theory as a collection of definitions and theorems, we can see it as a small number of recurring ideas. Collapse, preserve, act, count, decompose, represent, classify. And now, as we close, let the main thread rest clearly in memory. A normal subgroup is a compatible subgroup. A quotient group is the result of collapsing it. A homomorphism collapses its kernel and remembers its image. The first isomorphism theorem says that quotienting by the kernel gives the image. The second and third isomorphism theorems organize the behavior of subgroups and quotients. Direct products build groups from independent parts. Group actions turn groups into motion. Orbits measure where points can go. Stabilizers measure what keeps them fixed. The orbit stabilizer theorem counts the balance between movement and symmetry. Permutation groups make group actions concrete. Cayley's theorem says every group can be represented by permutations. Sylow theory studies finite groups, 2' power subgroups, using existence, conjugacy, and counting. All of this is one course in structure. Slowly, patiently, group theory teaches us that symmetry is not vague. It has algebraic form. It can be collapsed, mapped, counted, decomposed, and represented. And in that careful structure, we find a quiet and durable kind of understanding.